for several generations of parallel machines, every time you give scientists a new machine, they would be able to just expand the resolution and occupy that machine. That's no longer the case. You're kind of, in many applications, you're at the end of that kind of scaling, and you want strong scaling to get the same size problem running much faster on bigger machines. At the same time, the machines themselves are becoming more complicated. They present all kinds of variability, static variability, and dynamic variability, and so on. Temperature issues, energy issues, they're all kind of complicating our life as programmers. So what the CHAMP++ approach is not full automation. It's not full burden on application developers, but rather it is a good division of labor between the programmer and the system. So how does CHAMP++ do it? Well, the first order, CHAMP++ is a general parallel programming model. It's not a domain-specific model. You can think of it as an alternative to MPI or UPC or Chapel and so on, but it's not an alternative to C++ or Fortran or something. It's not a language in that sense. It represents a style of writing parallel programs. It includes an adaptive runtime system, and it includes an ecosystem around it, which includes debuggers and performance analysis systems and so on. So there are three concepts at the basis of CHAMP++ that you should understand. So the first concept is over-decomposition. Over-decomposition is the idea that you decompose the work units and data units explicitly. It's not going to be automatic. The programmer is going to do the decomposition, but they are not going to do the decomposition to the number of processors. So that means they're going to make maybe lots and lots of pieces. If there are 1,000 processors, you may make 10,000 pieces of work, for example. So this is not so hard. You do decomposition anyways. You just overdo it. So that's first thing you do. And the second thing is at the basis of the system is you make these work units and data units migratable, right? What does that mean? That means the programmer does not think about the physical processor. So you address your communication to the logical entities, not to the physical processor, right? That's a good thing, one less thing to worry about. But for the runtime system, it's a little bit of a headache. It needs to keep track of where each unit is, and it needs to do naming and location management, which it does well. That's one of the things that's built into CHAMP++ system, so it knows where each object lives, for example. The third thing is asynchrony, and you have many units on each processor. Many objects are sending method invocations towards them. Well, they need to be scheduled. So the scheduling can be done under user control or under system control. And we say, no, not under the user control. User doesn't say, next run this, because the thing that you're talking about running may not have all this data available. So we say, scheduling, let it be the choice of the runtime system. The programmer only says what's available, and then the system picks what's ready to execute. This is called message-driven execution. Now, so these three ideas are realized in CHAMP++. The over-decomposed entities in CHAMP++ are called chars. Char is just an old English word for chore, but in our case, it means a C++ object. There are methods on objects, and some of the methods are designated as entry methods for chars. In fact, that's a distinguishing feature of a char. A char is a C++ object which also has entry methods. And entry methods are methods that can be invoked from remote processor, potentially from remote processors. So chars have entry methods. Chars are then organized into index collections. We'll come to, in the second half of the talk, to index collections, but each collection has its own indexing scheme. It can be one-dimensional, three-dimensional, sparse, or dense. And then chars communicate with each other via asynchronous method invocation. That means I invoke a method on this object. In normal sequential means I get a return value back. That method runs, I get a return value back. Here it means I send a method invocation towards that object, and at some point in future it will execute. All right, I continue doing other stuff. If it wants to give me something back, well, it will invoke another method in my object later on. All right, so that's asynchronous method invocation. So if you look at this picture, this is an ocean of objects. A parallel program consists of a whole bunch of objects. In case of CHAMP++, the program consists of sequential. Some objects are globally visible objects. Let's say those are globally visible objects. The other objects are just your usual sequential C++ objects, right? And so those sequential C++ objects are just owned by the globally visible object. One or the other of them will own it. And so in object orientation terminology, that will be a has a relationship. Each parallel object has a 1 or more or 0 sequential objects attached to it. They all move together. Now, if you just focus on the globally visible objects, then the runtime system is going to partition them. The user's view is just that of the ocean of objects. The runtime system is going to partition them into processors. In this case, I've shown only 4. And then it's going to say, okay, well, now I need to execute things. There's going to be a user level scheduler on each processor, and there's going to be a queue of method invocations that's waiting to be executed on each processor. So specifically what happens when you invoke a method, let's look at an example. The processor on the left, the orange one, let's say, wants to invoke a method in 23rd element of the object collection A. So it simply says a sub 23.foo and some parameters and makes that call. The runtime system says, oh, that's what you want to do. It will package up that into that little green packet shown there and serialize it, put the information there, and then figure out where that object lives as of now, sends it to that processor, and that packetized, that serialized message just sits in its envelope inside that scheduler's queue on that processor. At some future time, the scheduler, this packet comes to the front of the queue. It picks it up and says, hey, is the object still here? If it is not, it might have migrated away. I'll find out where it is and send it there. If it is still here, which is most likely the case, you invoke the method, let it run to completion, which will create more such method invocations for other objects, which will be sent towards their destinations, and the execution continues in that fashion. This is the entire execution model. Well, let me say one more thing. You then notice, the runtime system notices that some of these objects are fatter and some are thinner in terms of the computation load they represent, or maybe memory, maybe communication, and the runtime system is watching them execute, and then it says, oh, I need to move things around. I need to move work away from this processor. Oh, this object talks to more objects on that processor. So it can take communication into account, computation load into account, and move things around to effect optimization. So this is the entire execution model of CHARM++. And this is something that's roughly, CHARM++ came about in about 93 or so, the name, but most of the concepts are stabilized around 1998, 2000. So it's a really old model, but it is really modern in terms of its applicability. And it's kind of like an old idea, which was well ahead of its time, but now we need it. You'll see why. Once you have these 3 things, over decomposition, migratability, and asynchrony, and you add to it an introspective runtime system that can adapt to what's happening, you get an adaptive runtime system, which can do a variety of things like dynamic load balancing and so on. Let me show schematically here. With over decomposition and message-driven execution, you enable a variety of things like automatic overlap of communication and computation, compositionality. I'm not going to go into all of the details. With migratability, you can do fault tolerance. With introspection and adaptivity, you can do dynamic load balancing. You can do automatic power and temperature control. Just a couple of those concepts I will illustrate. So, for example, here, there is now a lot of activity around multi-cores, many cores, accelerators, and so on. Well, locality that objects connote, CHARM++ objects, you work, an object is allowed to work on only its own data. Anything else it needs, it has to get it from method invocations. And so that connotes a locality, and that's always helpful on all of these architectures. More interestingly, message-driven execution, the scheduler has a peek at the queue. Right? It knows what's the next thing to execute. It also knows what are the next 5 things to execute. It can prefetch the data needed by those. How does it know the data? Well, it knows the data because every object's data is that object's is all that is a method invocation is going to touch. And so it can prefetch data into, say, scratchpad memories or HBM, the high bandwidth memory from the DRAM. And so these kinds of movements can happen automatically because of the ability of the scheduler to peek ahead. You look at communication. If in a typical MPI program, well, somewhat caricatured, you get compute, communicate, compute, communicate, right? Represented here by the red and white. You actually might say, well, I'm spending 30% time on communication, and if you understand some of these optimization techniques, you might move some sends up, use I receive and wait alls, and so you will say, well, now I'm using only spending only 10% of time in communication. You're happy, but really you are wasting the communication network 90% of the time. Isn't that what that means? And we worry about floating point utilization so much, why don't we worry about communication network utilization? So instead of reducing time on communication like that, what over-decomposition does is it spreads the communication over the entire time step. Right? So one object does its work, sends its data out on its way, while another object starts executing, sends its data afterwards, and by the time you're ready for the next iteration, the first object already has its data from whoever is sending it. Some objects has its data, and it can continue working. So the communication spreads over the entire time step, and you get an automatic adaptive overlap of communication and computation. When we typically decompose problems in the traditional method, you decompose them to processors. Let me give you an example. So this is an example from a rocket simulation thing, but very generic, generically speaking, fluids and solids, right? And so typical thing is to partition the fluids mesh, which might be a structured mesh, into P pieces, partition the structures mesh into P pieces if there are P processors, and put the 17th chunk of the fluids mesh and 17th chunk of the structures mesh on processor rank 17, simply because their partitioner called them 17th. Right? There's no geometric connection between them, anything like that. And so instead, with CHAM++, what you do is you decompose the solids mesh into maybe n pieces, but fluids mesh into m pieces. Doesn't have to be the same. And they are just logical decompositions. They talk to each other. The runtime system figures out whether they should go on, which one of them talk to each other more, which one execute concurrently or one after the other, and accordingly figure out what lives on which processor. Right? So you are freed up from that task, and the system can optimize things better. So then CHAM++ is a way of parallel programming based on objects, over-decomposition, asynchrony, migratability, asynchronous method invocation, which is the messages, and an adaptive